welcome to today's session where we're going to be taking a look at how we can implement maths in our FPGA design. If somebody could just ping me a message and let me know in the chat that you can all hear me okay, that would be wonderful. Excellent, and hopefully you will be all able to see my screen in a second when I flip these two, when we flip these two over. So today we're going to take a look at how we can do maths in FPGAs, and this is really important because it's one of the key technologies that we need that really makes FPGAs really beneficial for. We're going to take a look through at several different aspects of this. So let's take a start, and we'll get through. As we're going through this, if you get any questions, please put them in the chat, and I will keep an eye on that, and we'll try and answer it. As always, at the end of it, this is all going to be recorded, so you'll be able to see it via our website, via our YouTube channel. And there will be a GitHub being created slightly later on this evening, which will include all of the examples that we presented today, the slides, and all of the Vivado projects. The ones probably slight exceptions to that is the MATLAB project, but everything else will be there and presented for everybody to take away and reuse. So let's make a start. So today we're going to take a look at why we might want to use maths in our FPGAs, where we want to use maths, the difference between fixed and floating points. We're just going to touch a little bit on that and see how we actually do that, and then we're going to take a look at why more often than not fixed point is better to implement our tools with. And then what we're going to do is we're going to take a look through some examples. So we're going to take a look through a simple example in Vivado, a more complex example in Vivado, and then we're going to take a look at how we can implement these things in different ways. So having taken a look at a simple example in Vivado, a complex example in Vivado, we'll then take a look at how we could perhaps use high-level synthesis using Vitis, HLS to do, and we'll take a look at a PID example in that, and then we'll wrap up with taking a look at how I've used MATLAB Simulink to create an IP module that we can drop into an FPGA as well. If I'd have been slightly more switched on this morning when I got up, I would have brought the board in with the example on it for the MATLAB Simulink one, but I was a little sleep deprived, so I didn't. But yeah, as we go through this, please ask any questions. So think about over my career where I've used FPGAs, and most of them have relied upon me to put mathematics in there in some way, shape, or form. So, for example, in image processing, we might need it to do noise removal. We might also use it to do things like edge detection, such as Sobel edge detection, or more complex filtering that we put into our FPGA. If we're doing things such as radar processing or signal processing, then we want to be able to generate signals, and we also want to be able to process the replies when they come back, be that either filtering, manipulation, FFTs, and such like. And all of these require some elements of mathematics in there. We could also, perhaps if we're doing robotics, you might have noticed on my Hackster channel, I seem to have a lot of robotics projects ongoing at the moment that keep dropping out there, and that's because they're quite interesting and fun. So we can use mathematics in robotics to work out the end effector positions, or navigation, or understanding our environment. As you'll see later as well, in the control system area, we might use PID loops. So there's a lot of things we can do, and obviously, if we're doing motor control, then we may be doing things such as vectorless motor control, and so on. And that again requires fundamentally a lot of maths that are building blocks. So all of these require us to understand the basics about how we can go away and create mathematical applications in our FPGAs. And it's going to be quite fun to work through. So we can have a lot of fun, and just some examples of some projects you can find on Hackster and walk through. We could do examples of where we might want to use mathematics, background subtraction and removal from image processing. So in the one over there, you can see me doing a sort of cloak of invisibility or chroma key type things. We might want to do it, as I was saying, for image processing, where we want to detect edges, such as we can see in the edge detection. We might want to just have some fun and experiment with fractals. or as we see now in a lot of applications, AI, ML is really important and is a key element of that. So the slide should be on the main screen. Is everybody seeing that, or are they? Let's do this. Let's just go back and do this, and let's see that they're on the main stream for everybody. But as I was saying, the AI ML side of things is the key aspect. I think. Sorry, Jimmy. I think there might have been some sort of weird little glitch with the system, but hopefully it's a little better now. So obviously AI ML relies a lot on mathematics, as does signal processing. So what we're going to do is we're going to take a look at why we might want to do this in an FPGA. And obviously FPGAs, they're fantastic. They're fantastic devices, but they are really register rich. So we've got a lot of registers and logic in our FPGA. So we've got lookup tables, distributed RAMs. They're designed really to give us high performance implementation of logic. And traditionally, when I started doing FPGA design 24 years ago now, just as the Brontosauruses were still walking the earth, it feels like, in terms of FPGA design, this was what we had to create our mathematical operations out of, our mathematical elements out of. Was just those CLBs, those registers and such like. These days, we're a lot more blessed in our FPGAs because we have DSP elements. The most popular one that we'll come across in the AMD series is the DSP-48, and that's really optimized for doing fixed point mathematics. As we talk more, and we'll do some more webinars next year on Versal and Versal Edge, we'll see that there's the DSP-58, which is also really good for not only fixed but also floating point. But these DSP elements, they're ideal. And if you've been on our other webinars that we've done recently, they're ideal to allow us to create not only high performance applications, but also allow us to easily achieve timing performance and timing closure. Now, one of the nice things about these is we can use them as addition, we can use them for multipliers, we can use them for the multiply accumulate, as we'll see later on, and we can do some really interesting things with them. We're not going to touch on it too much in this webinar, but we can do things just like you can in software, where you might do single instruction, multiple data to make sure that you get the best out of it, the most efficient implementation out of that particular DSP element. So our FPGAs, they're really great for doing this implementation of logic in parallel. But what we want to do is, if we think about just what we've just talking about, the logic, the DSP elements, ideally they're great for doing what's called a fixed point implementation of mathematics. So we're just going to touch very briefly, before we delve into the examples too deeply, the difference between fixed point and floating point maths, because it's quite important, and it's a key thing to estimate and understand how it all works. So if we have a fixed point representation when we do fixed point maths, it means that basically we're defining a point between two registers and saying this is the place where the decimal point lives. Now, this is, as you can see in the example below, the 16-bit register. What we're saying is everything to the left of that decimal point, that's the integer element, and to the right of that is the fractional element, and that's how we can represent our numbers. We can have an integer point, we can have a fractional point. We can say this is the decimal point between the two, and we can then effectively work with that. Obviously, the major drawback of that is that we can't store a huge range of numbers in a fixed point number system like we've got with the 16 bits. The larger number system that we want to use, the more precision that we want, the wider range of numbers that we want, means we need to have more registers. But actually, we're using FPGAs, so that's perfectly fine, because the one thing FPGAs are is they're register rich, which is why fixed point number systems map really nicely to the FPGA environment. Now, one of the formats that we might need to do this when we're talking about this, and we're going to come to this in the examples later on, is when we've got a vector such as this and we're defining where to put the decimal point, we need to have a standard way of communicating with other engineers and ourselves when we come back to look at that project in 6 months' time, where the decimal point in it is. So we might say that we could use the Q number system, which is quite a common way of representing this. So we might say this is a Q8 number. So the 8 being the 8, there's 8 fractional bits. So the first 8 elements are the fractional bits, and then from the 8th one onwards, it's the integer bit. We might say there's a M of n, so we might say it's a 16, 8. And that way we know that the vector is 16 bits long, and there are 8 fractional bits. It doesn't really matter which format we use, so provided we use a common format, and provided that we stick to that standard flow as we go through. But using a fixed point number system can cause us some issues, as we're talking about. It can cause us the issues when it comes to quantization and how we store the numbers, and we'll come to that in a second. Obviously, the opposite thing of a fixed point number system is to use a floating point numbers. In floating point numbers, you know, the most common one of these is the IEEE 1754 standard. That defines a 32-bit vector upon which there is a sign bit, there is an exponent bit, and a mantissa bit. And as you would expect, it floats to where the decimal point is, floats depending upon the mantissa and the exponent to give you a wide range of numbers. Now that's really useful in a software world because you've got a 32-bit vector. You don't need to go any wider. Okay, sometimes we go to 64, but within that 32-bit vector, we can address and store a wide range of numbers because of that floating point element of it. The problem is within the FPGA, obviously, this becomes more complicated to implement if we want to do a number system. So fixed point works a lot better and gives us a lot higher performance than perhaps floating point implementations do. So fixed point is it's my preference. It's how we tend to implement things. Although you'll see in a moment as we go through and get to some examples, there are examples where we've had to use where we've used floating points. But the fixed point is because it's less complex to implement in the logic. You know, it makes it easier to implement in the logic. There's less routing. There's less connections. It provides us with a much faster solution, and it can actually be power efficient because we're taking advantage of the FPGA's register-rich environment. And because we've got this sort of, as I was talking about, we can have a standard format to define where these numbers are. So we can have a Q15 or an M of n, as we were talking about, just to define where that decimal point sits. Because we do, hopefully I'll put the slides in for that, because we do need to know that, because that becomes important when we want to do operations upon our vectors. We need to know where that decimal, unlike with floating point, we need to know where that decimal point is. So we'll take a look through that. How we represent these in our FPGA, obviously, it's relatively straightforward. We're not going to use sign and magnitude because that would give us the problem of having a positive and negative 0, which complicates our mathematics, which means that we need more logic in there, which means we need more routing in there, which impacts our performance in the FPGA. We could use ones complement, but again, that causes us a problem with doing subtraction, because it means we have to do an end around carry, which adds complexity. So by and large, most of the FPGA languages that we use, they represent numbers, signed numbers, using A2's complement scheme. And that makes it really simple to do. So Sam, I'll come to your question in a second. It doesn't actually need way more. It doesn't actually need way more resources than a floating point and a floating point one would do. Typically, floating point use more. What I will do, because I don't have a direct example of this, but what I will do is I will create a blog using some of the libraries I'm going to show you in a little while, and I'll do a comparison between doing a fixed point and a floating point, and I'll throw that in a few different FPGAs as well. So I'll do it in in like an Artix, an Ultrascale, and then I'll throw it in a Versal as well, so as we can see what impact comes when it maps to a DSP maps to DSP58. So by far, all of our number systems in our FPGAs, when we're working with standard logic. Yeah, Jimmy, I thought about that. I'll do the DSP58 as well. When we work with signed numbers in logic, it's going to be using a 2's complement representation to allow us to do that. A 2's complement representation, if you're not familiar with how to do it, we can cheat. The simplest way to do it is to invert the number, and then you get to the first one, working from least significant bit to the most significant bit, and then just invert every other bit after that. But it's going to give us a range of numbers, so where we can go from 2 to the n minus 1 to plus 2 to the n minus 1 minus 1. So it's going to give us a nice range of logic that we can, a nice number range that we can flip between and represent. Venkat, I'll come to your question in a second because I think it's important. But let me just get to wrap up this, and then we'll talk about that. So one of the things we have to think about, the really important thing we have to think about with fixed point numbers, is how do we quantize them? So the easy bit is for the integer bit. We can quantize the integer bit easy. So if we say we want to quantize the number 423, most of us in our heads can work out that 9 is the number of bits we need. But there is an equation that we can use. We can take the ceiling of the log 10 of the integer maximum divided by log 10 in 2, and that will give us the integer bit that we need. Once we've got that, we can then work out how many registers we need to store our integer bit. Storing the fractional bit, however, can be a little bit more complicated. And that's typically what we work with in FPGAs, because if we're working with filters or averages or things like that, we end up with working with very low fractional numbers a lot of the time, such as this, 1.45309, blah, 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 times 10 to the minus 4. How we would go about quantizing that is to multiply that by a power of 2 and say, well, that's the number of registers that we need. We'll multiply that by a power of 2 and we'll store it in here. So if we wanted to represent this scale by 2 to the 16, we could do that. But we can't, and that gives us the 9.523023 answer. But we can't store the 0.5 in our FPGA. We can only store the 0.9. So if we store the 0.9 and then we do the divide by 65536 again to actually work out what it represents in our fractional number, that's only 1.37. So that loss of precision might cause us issues and challenges. So what we need to do is we need to think a little bit more about how we can address this. But because FPGAs are register rich, we can scale these numbers however we want and store them within our FPGA. And sometimes it doesn't even need that many registers to actually store it in. We just need to know that the number has been scaled by this, and we can store this number. So for example, if we multiplied this by 2 to the 20, that number by 2 to the 28, we just need to store the number 39,006. And if we divide that back again and go back and work out, and we should always do that when we're doing quantization, if we do that and go back, we'll see that actually now we store a number much closer to what we want to do. So we can say that if we store the number, we can store the number 3006, and we can put a comment next to it at the back end of it saying this number scaled Q28 or 1,28, and we know that where the decimal point is within that, if we do any more mathematics or mathematical operations on it. So once we've stored our number, so we have a number of challenges. The first one is to work out how to quantize our number, and then we store that number in our flip-flops and our registers. And like I say, I will make available the demo examples that we've got for this, as you can look through the code and do it. They're all going to be in VHDL for one particular reason, which we'll explain in a second. But once we've got those numbers stored, we want to be able to do, addition, subtraction, division, multiplication, all the things that we want to do on an FPGA to be able to do this. And there are some rules. So if we're doing addition, we need to make sure that the decimal points are aligned, which is why we need to know where the decimal point is. It's the same for subtraction. It's the same for division, although typically we'd write a divider or find a divider IP code. For multiplication, it's going to work out. It doesn't matter it doesn't matter that they're not aligned, but we have to make sure that they're aligned for all other operations. Obviously, because we're working with with registers, and the decimal point is not floating like in the fixed point world, in the floating point world even, we get a larger result. So if we add two 16-bit numbers together, we will get a 17-bit number as a result, because if they're both at the maximum value, then that can't be contained within a 16-bit number, so it needs a 17-bit number to store them. Similarly, for if we're doing subtraction, or let's just skip the multiplication thing for a minute, or if we're doing division, so the number may grow by the vector the result vector may grow by 1 if we're doing addition, subtraction, or division. If we're doing multiplication, the result will actually be a vector that is twice as large as the largest vector that we want to multiply. So if we multiply two 16-bit numbers together, we will get the result as a 32-bit number. Hopefully this makes sense to everybody so far. And this is one of the challenges when we're doing FPGA maths, is we have to make sure that we get the right format, we get the right resultant vector to store the result that we want. If we get it wrong, the synthesis tool might complain, or it might not, and we might get the wrong result out of it. So when I do maths in FPGAs, I tend to use VHDL, not Verilog, and there's a reason. The reason for this is pre-2008 for VHDL 2008. There was a numeric standard package which you could use, which would give you the signed and the unsigned types. But to do that, we'd need to keep track of the decimal point, where the decimal point is in the vector. We'd have to do the quantization ourselves. We'd have to take that number from our example, the 1.45 times 10 to the minus 4. We would have to multiply that by 2 to the 28 that I said previously, and store that number in a vector. And then there's no real checking for any overflow or underflow that might be in there. Post VHDL 2008, they introduced a package called UFixed, and they also introduced a package called a floating point package as well, which is what I'll use for my example when I come to it. But in that package, they defined two types. They defined a UFixed package and an SFixed package, so they're a signed and an unsigned fixed vector types. And with the UFixed and the SFixed, the decimal point always relates between the 0 and the -1 bit. So in previous worlds, and you'll see this in an example in a minute, where we would have a vector that went from, say, 15 to 0 for a 16-bit number, even if it was 8 bits integer, 8 bits fractional. In VHDL 2008, if we have a UFixed type, we can go from 7 down to -8 in the vector, with the 0 to 1 bit being where the decimal point is. So it's very obvious where the decimal point is. It gives us the ability to do it gives us the ability to make sure that the checking is correct and handle overflow and underflows and all those sort of things. So it's a very useful package for writing examples. And the examples you'll see today and I provide on the GitHub, they're made using that standard. So for an example, we can represent here, we can have an example here where the UFixed bit is 2 down to -3. And that gives us a range of numbers that we can go between 0 and 7.875 in a unsigned vector format. And of course, it gives us all the things that we can use to translate between signed and unsigned. So it's really nice and powerful, and to go between vectors, reals, standard logic, and everything, just like you'd expect. It gives that ability to do that transaction. So let's take a quick look at that in Vivado. if I could get that to minimize, I have my Hackster Math project open here. So this is a VHDL project. I'll make it available to you all, and it's just doing a simple accumulator. So it's storing 10 values, and then it's giving the average of the 10 values out. Obviously, I don't want to use a divider in this to do the divide by 10 because that requires a lot of mathematics. So because the division is fixed, I'm always doing a divide by 10. What I actually do is I do the accumulate, so add all the 10 samples together, and then I do a multiplication by 1 over 10, so the reciprocal of the value. So we can see here it has we use a constant for the divider. We're using the unsigned type, the unsigned fixed type. It's purely fractional number, so it's a -1 down to -16. And I can use the toUfixed function to say, actually, I want to quantize this value 0.1, and here's the upper and here's the lower bounds that I want you to quantize it into. And then we just have the normal, the normal vectors, the accumulator, the actual average result. Obviously, that grows as we're doing the result. And then we have the maths here. It's just doing it on a clock cycle by clock cycle basis. I give you a test bench. I'll give you a test bench with it as well. And then obviously we can simulate that and run that through. So no, there's not a value of doing there's not an equivalent of doing this in Verilog or System Verilog that I'm familiar with, but typically I do more VHDL than Verilog, so maybe there is, and if anybody knows better, please comment, because I'd be interested to know. You can run that through in the simulator. I'm not going to spend a lot of time on it. Yes, Vivado does support 2008 synthesis, all these example synthesis, but you've got a test bench that you can take a look at, and you can work through an experiment with. If I come back to my presentation, I swear my computer runs very slow when it's sharing screens. So if we want to implement complex functions, so now we know how to do simple things such as addition, subtraction, multiplication. We might want to think about how to do transcendental functions such as sine, cosine, exponential, square root. We could do this using lookup tables, from Maclaurin series, etc. But one of the more common ways to do this is to leverage the CODIC algorithm created by Jack Volder for the B-58 program. Really cool looking aircraft there, and it's a shift and add algorithm, so it doesn't require any dedicated multipliers. It was what led to the first, that algorithm, and LSI, such like modern semiconductors, led to the first HP35 scientific calculator that could do those functions as well. If you've never come across it, there are some blogs on my website talking about the exact algorithm itself. Initially, it started out in what's called the circular mode. That was the original derivation of it that would allow you to calculate the sine and the cosine, or to do the arctangent or the square root. But over time, it's been expanded to be able to do linear operations and to do hyperbolic operations. So if you're in a very small constrained device, you can do multiplication or division by doing just shifts and adds in the linear rotation. But the important thing is we can do this to get sines, cosines, tangents. We can calculate exponentials with this, natural logarithms with this, and of course we can calculate square roots. When to use CODIC or when to use lookup tables, I'll come back to at the end, because I'm now a little nervous that we're not going to get through everything in the time. But essentially, it comes down to your experience and what you need to do. A CODIC can actually be quite small and cover quite a range of things. But there's nothing wrong with lookup tables neither. One of the big decisions would be precision. Because obviously lookup tables just give you discrete outputs in between this value and this value. You've got lookup tables that drop out particular values, whereas with a CODIC, it's a much smoother and a much finer granularity of it. So by doing simple mathematics, you know, we've now got to a position in our speed FPGA class on maths that we now know how to do subtraction, addition, division, multiplication. We know how to do square roots, sines, cosines, tangents, and such like. So we'd be able to implement the following algorithm, right, relatively easily, which is a algorithm that you find commonly in applications for doing platinum resistance thermometers and converting that into a temperature value. Now we could do this in our FPGA. We know everything at this point. We know how to do it. But there are some tips and techniques that we should do if we're going to go away and implement this. And the first one of these is we should be sensible and plot the curve. If we plot the curve, we might find that actually it's nearly linear, but it's not quite linear. So what we could then do is we could work out the polynomial equation for that. It's much easier to implement this equation in our FPGAs than it is to implement this. We work many less weekends if we don't have to implement that, but we can implement this. And this is relatively easy. Again, it's addition, subtractions, multiplications. It's relatively simple, and we know how to do that. If we get to a point where we have, for example, an element that doesn't easily give us a plot, what we could do is we could break that curve down into a number of segments and generate a number of coefficients to allow us to just address that segment. So if a value is between x and x plus 1, we use these coefficients for our polynomial. If it's between x plus 1 and x plus 2, we use these set of coefficients for our polynomial. And we did that actually on one of our space programs for the European Space Agency's Plato mission. We used a similar approach for measuring temperatures to give us some really supreme accuracy. We use sort of like a uniform segmentation approach to get that value out of there. So those are really fun things that we can do with our FPGAs to give us some maths. So if we just come back now, just quickly show you a more complex example in Vivado, and the screen might be a little bit zoomed out, but you can get the examples later on. But this example is actually, this is the code that implements the example you've just seen presented to you on screen. So, for example, we have the A, B's, and C's. We have some constant coefficients defined in there. We've used the sign type because we're working with sign numbers. We've used the quantization, and then I've used a simple little state machine just to run around and drop it out. What I will do as well, there's a spreadsheet with this which shows all the calculations for it. I'll provide that. And there's also a test bench. But you can see it gives you a little bit of code that you can simulate through and look through. So there's a nice example there of how you can do that complex FPGA algorithmic implementation using polynomials. The other area that we tend to use a lot of maths in FPGAs is filtering. Now this is where the DSP elements come in brilliantly because they do that multiplication and accumulate. But if we just think about the filter for a time being, you know, a finite pulse response filter, we want it to be pretty much a brick wall. If we were to take a inverse FFT of that brick wall from the frequency domain and plot it, we get this windowed sinc function. These points on the windowed sinc function are what actually become our coefficients that we might use in our filter design tool, be that MATLAB or one of the free online things. What I will do is I will put some links to some Hackster projects we've done about filtering in there. Now, sometimes for filtering, we want to put some those ripples on the end. They ripple on forever. They get smaller, but they ripple on forever. So we might use a window and try to window our sync pulse. And typical windows that we might apply might be the Blackman or the Hamming window to that. And if we were to look at that in our FPGAs, then when we run this through, we will see a much smoother, rather than having this ripple that we get from having an untruncated sync pulse, we get a much smoother passband and stopband. The difference is on the performance during that transition band. So understanding fixed point maths really allows us to be able to design filters and work with filters and leverage those DSP 48s that we have in there. There's a couple of ways you can design these tools. There is one that's free online called T-Filter. It's web-based. You can go to it. You can just put in the parameters that you want, and then it will drop you out the filter. It will drop you out the filter coefficients, as you can see there on the left. If you drop down that little drop-down menu, it will actually quantize them for you as well into like a 8-bit or a 16-bit number that you can put into the AMD filter design tool. But essentially, we can take these values here and we can drop them in the quantized ones into the filter compiler and build that and run that through into our AMD designs. And like I say, I don't have much on that just because I had to work out how much to keep up not putting this out as webinar. But there are 4 or 5 projects on Hackster that we've done where we talk about how to design filters and work through them. But it's understanding how to generate these coefficient vectors and quantize these coefficient vectors is really important and a key for our FPGA designs. And if you take a look at that, if you want to take a look at that, we can see, for example, filters running with a nice simple passband, with it passing a 10 megahertz filter, or then actually moving the signal up to 25 megahertz so it falls into the stop band. So what I've presented so far is that we've used RTL source code to create and implement our mathematical algorithms, and there's nothing wrong with that. There's probably, when it comes to working with high-level tools, while they give us abstractions and productivity improvements, the resultant code is probably not going to be as performant as what we could get if we wrote it by hand. The question really becomes, do we really need to write it by hand to get that performance? So one of the tools that we can leverage is the Vitis HLS, and that allows us to take our untimed C and move that into timed RTL, either VHDL or Verilog in this instance, because that's what dropped out. It's not very good for the control plane, but for the signal generating, data processing plane, it's really powerful. I'll fix that. I'll fix this one later. I didn't realize this, but essentially it allows us to go from untimed C, where our simulation time is much faster, into a verified design a little bit quicker, because what we do is we can iterate faster if we're working in C, and then we can move into we can do the synthesis to RTL, and then we can start testing on the hardware. Couple of caveats with this. I'm not going to go through it all, but software that's written for C, for our computer, our CPUs, our micros, is very different than C that's written for HLS, and you've still got to think about it. Quite a lot. We need to focus on, when we're writing C code for synthesis into FPGAs, you've got to think about the producer and the consumer. You've got to think about decomposing the algorithm to as small a section as possible to do that. And we've got to make sure that we focus on throughput. I'm not going to talk too much about HLS and how to do it. We did a webinar and a couple of workshops on it. So in the same place you'll be able to find the recording of this, you can go back and see a full 2-hour workshop on how to work with HLS. The example I'm going to present is actually the same one that was in one of those workshops. But our design flow is essentially we create our C model, we create our C test bench, and then we prove that the performance of that is how we want it to do. Once we've got that, we can synthesize, we can convert that C into RTL. We can optimize the interfaces for our synthesized implementation. We can make performance optimizations as well with pipelining, unrolling, and such like. And then we can do a co-simulation to prove that our RTL that's generated by the synthesis tool behaves the same as our C that we've created. And by the time we get to that, our final stage then is to take it and package it and use it either in Vitis or in Vivado. It's really simple how it does this. It goes through a couple of stages. The first stage is it goes through what's called scheduling, where it works out what clock cycle to do a particular operation on. So you can see in this one, it's working out that it can do the A multiplied by the X plus the B, but there's not enough time to do the operation with the C, so that gets done on the second clock cycle. Once it's worked out the scheduling and the order of events, it's going to bind those to resources in the FPGA that you're targeting. So it's going to bind these to registers, lookup tables, DSP48, BRAMs. And then once it's done that, it's going to pull that through and it's going to create a control logic section around it to be able to actually control the functionality of that block as it actually operates in our design. So that'll include starting, stopping, saying it's busy, saying it's idle, and all those things. And what we can do is we can easily change these interfaces to be not only discrete logic vectors or logic vectors with valid signals, but we can easily, one of the benefits of HLS is we can easily change these to have AXI interfaces, for example, or BRAM interfaces or filter interfaces. There's a lot of simple things we can do with it. Now, one of the things that makes HLS so good is it's provided with arbitrary precision data types. So these are data types where we can use the AP integer or AP fixed, and they can be unsigned or signed, and we can have variable width integers or fixed point data types that implement in the logic of the FPGA. These are really quite powerful to do, and they allow us to do the same thing that we would do in our FPGA function in our FPGA. But in a slightly, if we were writing RTL, sorry, but in a slightly different way. Of course, actually, I'm not going to delve into it too much, but there's also a huge range of HLS libraries that can be used for DSP and Vision, for example, that will give you specific functions and specific libraries that are going to be used. So if we look at the HLS math side of things, if you want to look at it, there is a APU fixed or fixed type, and again, we can decide where the most significant bit is. We can define how many integer bits, how many integer bits we want, how many fractional bits we want, and we can define the quantization mode, whether we round to infinity, round to 0, and we can also define how we want to work in the overflow mode. So it's a really nice, simple way of doing it. You can see a couple of examples there. For example, 2, 0 gives us the ability to, A could be stored as 0.5 because there's 2 bits in there, two fractional bits in there. So it works really nicely to give us that functionality there. If we want to take a quick look at this, and I will provide this example as well, we also get a project here where we're creating a PID. So let's see if I can actually zoom in on that a little bit, maybe. No, but we have a PID here where we're using a data type that we've defined, and we'll look at that in a minute. And we're just running through and doing a standard PID algorithm. So we're doing the multiplications, the addition, and then we're limiting the output power depending upon the calculated value. This is all nice and simple, where it's just this multiplied by this. In our header file, actually, I've defined the AP integer types that I want. So, for example, I've defined some 16-bit ones, some 32-bit ones, and some 48-bit ones. Again, you've kind of got to keep track of the growth of the result, but it gives us a really simple, really easy, really flexible way to be able to do maths. And although we're not here to talk about that, this element here gives us the ability to easily change the interfaces on the FPGA as well. So we can change the interfaces from, for example, logic to AXI to block RAM to FIFO. So there's a range of applications that we can do that with. So far we've looked at how we might create these things using VHDL or Verilog, the basic rules of fixed point maths, and then we've looked at how we can do more complicated functions in the FPGA. We've just touched a little bit on HLS, and how we could use HLS to help us. The final thing I want to wrap up on this is we do a lot of model-based design, so we use a lot of MATLAB and Simulink, and of course this is available using the Vitis Model Composer as well. There are elements that you can do that if you want to. But just to wrap this up, I want to give you an example of how we created this using a to again actually do a temperature sensing application. So instead of doing the PRT algorithm that we did with the complicated example, in this case we're doing a negative temperature coefficient for Mister. We want to take its resistance value that comes into an XADC and convert that into a temperature value. Now the way to do that is actually two stages. We do this first stage where we take in the resistor value, or if we know the series resistance, we know the ADC resolution, the ADC value, and we implement this little bit of mathematics here. And then once we know the resistance of the NTC, we can work out the temperature using this equation. So this is if we have a potential divider, the R series as the top resistor, the bottom one is what we want to work out as our value, shall we say. So in MATLAB and Simulink, we could split this up into two elements. You know, the first element, we're taking in a 16-bit value that comes from the XADC. So the XADC was just set to monitor VPVN and just stream out VPVN values constantly. There's a valid signal to indicate when those values are valid. And then we pushed it through we did that calculation of the negative temperature coefficient resistance. And this is what can be seen here. So we're taking in a value here. It's a bit zoomed out. Actually, I'll show you the reality of it in a minute. But we're doing the division. The Zs are actually registers that are in there. We're doing a division, and then we're moving it through, and we're doing the input divide and the output divide against fixed values to actually get the final result that drops out of the FPGA. Now, all of this is in a fixed point number. Windows key and plus. Let's try that. Windows key and plus. There we go. Back to normal. I'll come. Oh, where's that? I'll come back to that in a second. Let's just zoom that in a second, and we'll see where that went, because that went a little bit weird. So we'll edit that out in the recording. But yeah, so we can see here that we've got the initial stage, the input division, the output division. Out pops from that is the final is the result of this element here, which is a signed a 25-bit signed element. Obviously, there's a valid signal coming out, and then we need to calculate the temperature. So we calculate that temperature by running through again. I do some registering. And then we do some maths in the chain. So we do some conversion from a fixed point to a floating point. We do the logarithms, the inversions, and then we finally convert back to a fixed point system at the fixed point output at the end. What this gives us is a nice IP core that we can drop into our FPGA, and you can see here. That this is just a nice simple IP block that gets dropped into Vivado, and then if we run it through, so you can see the board is a MicroZ board. We actually ran it on my little bit of logic down here with the negative temperature coefficient for Mister here, and then the actual calculation of the value coming out, the actual raw value and the scale temperature value. So it comes out to about roughly room temperature. Yes, it is. So if I click on this one here, what we can see is, so if I minimize that for the time being, maybe maximize that. Yeah, it's as big as it will go, unfortunately, on my screen. But yeah, so this is the actual This is the actual Simulink design. We can see the input divide that I was talking about, the output divide. If we go up a level, we can go into the calculate temperature block, and this time we can zoom in a little bit on it. So we can see we have the multiplication, the conversion, the natural logarithm, and then doing the where's the scroll bars gone on there? Yeah. Didn't want it to go there. We can see we can have the maths, and we can see it all running through there. We can simulate this. This is one of the nice things actually about using MATLAB Simulink, is you can simulate this very quickly, and we can put our values in. We can see our values coming out, and then we can do the HDL code generation by using our. That's going to actually generate the code. But if we click on the HDL code advisor or the settings, actually. We can see the code, and we can generate this code and do all the optimization and everything on it for the FPGA. Again, this was targeting a 7 series FPGA. It worked really nicely. I was a little like, will this work? Will this not work? But actually, it worked really nicely, and it came together. It came together pretty well. So I was quite pleased with it. We have some settings because obviously we're using the floating point element. So yeah, it worked really well in there. So I guess to summarize in the last few minutes, because it has been a bit of a sort of drinking from a fire hose in this session. You know, maths FPGAs are great for implementing mathematical functions and algorithms in there. There's nothing to be scared about if you see that. There's several ways that we can do it. You know, we can use fixed point. We can use floating point as well, although we tend to use fixed point. You know, the VHDL fixed library is actually really good and really powerful for making sure you get it right. But there's also higher level tools that we can use to help us generate mathematical algorithms, such as high-level synthesis using Vitis, or MATLAB and Simulink. Now, obviously, each one of these has its own pros and cons. There may be some costs associated with some as well, so you have to think about the costs associated. But realistically, this is what comes down to. You know, as an engineer, this is why what we get paid the megabucks for, is to be able to work out the most appropriate solution for the task at hand, to allow us to do that task in a nice, sensible, flexible, easy way, and deliver to the customer or the client a design that works. So I think I've talked for 55 minutes now or so on FPGA maths. Hopefully it's been very useful. We have another webinar not next week, but in a couple of weeks, on signal processing in FPGA. So working with how to work with ADCs and DACs. I'll come to that question in a second, Sam. Yeah, so how to work with ADCs and DACs. We're not going to use high-end ADCs and DACs for this example. We're going to use the XADC, and we're going to look at things such as how to work with normal ADCs and DACs, but we're also going to go away and create some examples, such as using Delta Sigma and PWM and such like in simple FPGAs to get there. So if you want to follow back the link, that's on the 21st of November, I think. Sam, the main reason we went for HDL Coder rather than Model Composer was I wanted a technology independent solution, and that was the main reason I picked to do it via HDL Coder. If you want to take a look at how you can use Vitis Model Composer, I wrote a blog recently, maybe the beginning of this year, that takes a look at using Vitis Model Composer with the Versal AIE engines, and how you can use those AIE engines for other things than just doing AI, but things such as FFTs and so on. So there's a blog on our website that shows you how to do that. If anybody else has got any questions, please type them in and let me know, and we'll try and answer them. Like I say, if not, there's another one in a couple of weeks. In about 2 hours or so, this webinar will be available on our website, so you'll be able to go watch it. I'll get all of the examples uploaded to GitHub, so there'll be a link from GitHub. If you just go to our website, you'll see under the workshops tab, you'll see one under there that will be called Magical Maths, and that'll give you a link to all of the GitHub resources, to the slides, of course, and to the recording. So Venkat, VHDL versus Verilog for fixed point representation. It's entirely up to you. You know, it's whichever one you're more familiar with and you're happier and easy to work with. Because we do a lot of work in the high rel space, I tend to prefer working in VHDL. So the VHDL is what my go-to would be. And I also happen to think those VHDL 2008 libraries, actually, if you're doing mathematics, are really quite powerful. So I would tend to sort of go that way. But it's really down again to whatever's easiest and simplest for you to use is the best, is the best approach to do. So as a beginner VHDL, it depends on where you're located in the world and what you want to do, whether you want to go away and learn languages. Oddly, VHDL is apparently the most popular FPGA language, but actually I think Verilog is more widely used across a range of industries, including the ASIC industry. So if you're in an area that uses that Verilog's quite popular and common, then I would use Verilog. Depending upon your area, I'd do a job search, see what comes up first, whether it says VHDL or Verilog, and go with that one. Learning both is important. Well, you've just got to learn one first, but once you've learned one, picking up the others are relatively easy to do. No problem. I'm glad. I hope you've all enjoyed this. I will end this now. Like I say, I'll get the webinar up so everybody can take a look at it. And I will say it again, as always, thank you very much for coming and listening to this webinar, and thank you very much for your support. And I will hopefully see you in a couple of weeks at our next one. Thank you very much.